Imagine tuning a machine learning model where every single test run takes hours on a cluster, or a chemistry experiment where each trial costs real money and a day in the lab. You can't just try thousands of settings. Grid search and random search would burn through your budget and mostly land on duds. So how do you find the best setup in as few expensive tries as possible? That's exactly the problem Bayesian optimization was built to solve. The whole method is a loop, and once you see the 4 steps, the cleverness of it really clicks. There's no magic here, just a smart way of deciding where to spend your next expensive query. Let's walk through one full turn of the wheel. First, build a surrogate. Since the real function is expensive to query, you fit a cheap probabilistic model, usually a Gaussian process, to all the points you've tried so far. This surrogate captures both a best guess of the value everywhere and, crucially, how uncertain that guess is. Then comes the acquisition function. This is the decision maker. It reads the surrogate and scores every candidate point by how promising it looks, picking the single best place to sample next. Popular choices go by names like expected improvement or upper confidence bound. Now you actually spend the money. You take that chosen point and evaluate the real, expensive function there, running the full training job or the lab experiment, and you record the true result. This is the one genuinely costly action in the whole loop, so every previous step exists to make sure you spend it wisely and not waste a single trial. Finally, you fold that new result back into the surrogate and repeat. Each round the model gets sharper, its uncertainty shrinks where you've looked, and the next pick gets smarter. Round by round, it homes in on the optimum. To really feel why this matters, let's contrast it with the search strategies most people reach for first. Grid search and random search are memoryless. They pick where to look next without any regard for what they've already learned, so they waste precious evaluations revisiting hopeless regions. When each try is cheap, that's fine, but when every query costs hours or dollars, that blindness gets very expensive very fast. Bayesian optimization learns as it goes. Every result reshapes its belief about where the good regions are, so the next choice is always informed by everything seen so far. That's what makes it sample efficient. It routinely finds strong optima in a small fraction of the evaluations blind search would need. So let's distill the approach into the 3 pieces that make it work. First, the probabilistic surrogate. It stands in for the expensive function, modeling not just a predicted value at each point, but also the uncertainty around it. That uncertainty is what lets the method reason about where it might be missing something good. Second, the acquisition function, which balances 2 competing urges. Exploitation says sample where the model already predicts great results. Exploration says sample where it's unsure, because a surprise might be hiding there. Getting that trade-off right is the heart of the method. Third, sample efficiency. By modeling the problem and choosing each point deliberately, it reaches good optima in remarkably few expensive evaluations, often a tiny fraction of what blind search would need. That's precisely why it powers automated hyperparameter tuning and experimental design across science and industry. Let's lock in the 4 ideas worth remembering. Bayesian optimization finds the best input to an expensive black box function in as few evaluations as possible, where you can only query, not differentiate. It keeps a probabilistic surrogate, usually a Gaussian process, that models both the predicted value and the uncertainty everywhere it hasn't looked. An acquisition function picks the next point by balancing exploitation, sampling where results look good against exploration, sampling where the model is unsure. That loop makes it dramatically more sample efficient than grid or random search, which is why it tunes hyperparameters everywhere. To keep learning ideas like this in plain language, swing by Standarity.com.